So actually, this is the second part for section 6.3. So previously we talked about just taking, let's say, graphing a function, perhaps taking the line segment connecting f of x to the x-axis and rotating it around the x-axis, and you form a disk, and that's called the disk method. So we're rotating it or revolving it around the x-axis, or maybe we're revolving around some other line. But there's something else we can do when we have like a base that have solids with a known cross section shape. And so, well, there example that right here is kind of a nice example because it's we can visualize it easily. Okay, so let's say you have in this case you have some kind of like cube, or but you have a rectangular base, and then when you take those cross sections, every cross section has the same shape. Right, the dimensions in this case they don't, but the dimensions may change, but the volume, the area for computing the computing the area of the cross section is the same problem, and basically the thing that's going to change is the is just the maybe the dimensions, and sometimes these can be hard to visualize, and so like here I'm not even sure I drew this. Here's like one from section 6.3. Okay, so we have a solid whose base is the triangle with vertices 0, 0, 7, 0, and 0, 7. So to me, you really need to draw that triangle. Some of you may be able to visualize it in your head, but I think graphing really is quite useful, solving equations and just a lot of things that we don't necessarily have to do it to get the correct solution, but I think it makes it just easier to get to the solution. Okay, so first of all, we just make sure we understand where this triangle lies. The base is at one corner is at 0, 0, the other one is at 7, 0, and the other one is 0, 7. So it's actually, what was an isosceles triangle? Oh, it's kind of our lucky day. Anyway, okay, so let's see here. Okay, so and then now let's look. We're not rotating around, so we're not actually rotating um, um, we're not rotating f of x around the x-axis. So in this case, what does it say? Use the general slicing method. That's where we use the known cross sections to find the volume of the following solids. We have the bases, the triangle 0, 0, 7, 0, and 0, 7. And now here's the important part when you're doing this problem, and whose cross sections perpendicular to the base and parallel to the y-axis are semicircle. So basically, by drawing, I have a hard time drawing this. So if you started here, you'd have like a semi. Of course, but it would be three-dimensional, right? It'd be perpendicular to the base, right? But it's a semicircle. And so the distance from the x-axis to the curve, that's going to be the diameter of one of the circles, right? So the length of the diameter, and then also we're not actually given the line that forms the hypotenuse of that triangle, but we definitely need to compute that. And so that's the line y, I have 2 points, 0, 7, 7, 0. So we just compute the equation of that line for the hypotenuse, and it's y equals minus x plus 7. Okay, so we take any point here, we go x to minus x plus 7. Okay, so the radius of any of the circles is minus x plus 7. I'm sorry, the diameter of any of the circles is minus x plus 7. Remember our shape, we have this triangle, and then perpendicular to the triangle, there are these semicircles, okay? But you have to visualize those being, coming out of your computer somehow, right? So it's not two-dimensional, it's a three-dimensional shape. So you have a base of a triangle, and perpendicular, you have all these semicircles. Okay, the diameter of one of the semicircles is, and so that's the diameter is minus x plus 7. You go out some distance x, the diameter of the semicircle will be minus x plus 7. So the radius is minus x plus 7 over 2. Okay, so the radius is minus x plus 7 over 2. And so we know the area of a semicircle is 1/2 pi r cubed. Okay, so in this case, so it's 1/2 pi, and our r is minus x over 2. And then, so we square that radius. Okay, so and so the area of the semicircle is 1/8 pi times 7 minus x squared. And now we just integrate that from 0 to 7, and that's going to give us the volume that we want.